Okay, welcome back to the second part of this first lecture. So we talked a little bit about what we're going to use statistics for, which is to assess variability. But now I want to give two examples where statistical analysis can come into play. The first thing I want to talk about is how sometimes statistics helps shed light into or on non-intuitive phenomena. And to talk a little bit about that, we're going to talk about a classical statistics problem. It's not that old, it's a couple of decades old only. But it's a classical problem because I think every statistics course covers this or should cover it. And that is the Monty Hall problem. Now, if you've already read about this and you know the answer, I would ask that you refrain from spoiling it for everyone else. But obviously, feel free to answer at the very end. But if you do know the answer right now, let's just wait a little bit until other students try it out first. So suppose that you are on a game show. So you're a game show participant, and the host gives you a choice of 3 doors. Behind one of these doors, we don't know which one, is a car. Behind the other doors, we have goats. If you pick the door with the car, you get to take the car home. So obviously you want to pick the door that has the car and not one of the 2 doors that have goats. Let's keep that in mind. Behind one of these doors, there's a car. Behind 2 of these doors, there is not a car. Let's say you pick a door at random. Can somebody just pick a door? Any door? 2? Okay. So let's say we pick door number 2. That's our first choice. Now, if this were a traditional game show, the host would open the door and show you, congratulations, you won the car, or I'm sorry, you did not win the car. But this is actually a different type of game. Now that you've picked the door, the host, who knows where the car is, the host is going to pick one of these other 2 doors. And the host is going to open one of these other 2 doors, and it's going to show you that the door that he opens does not have a car in it. So let's say you pick number 2. The host can choose between 1 and 3. So the host will open door number 1 and show you that behind door number 1, there is no car. Okay? That's all that's happening. You pick the door, and then the host shows you of the other 2 doors, the ones that you did not pick, which one does not have a car. That's all that's going on. You know that that's possible in any case because there are 2 doors with goats and only 1 door with a car. Now the question is, should you switch your choice before the host finally reveals which door has the car? Do you want to switch to number 3 or do you want to keep number 2? Does it matter? Does it not matter, and why? So Marco says, I won't switch. So Marco will not switch. Marco will stay with door number 2. Anybody else?
I'm also gonna stay on door number 2.
Okay, stays for door number 2. Okay. But Alejandro says switch. Bailey says stay. Sarah says switch. Sean says switch. Okay, good. I like that we have this wide range of answers. It seems like half of you want to switch, half of you want to say, I know the answer, but I want to participate. Oh, Christian, just give me 5 seconds, okay? So some of you want to stay, some of you want to switch. Now, let's talk about it from statistical terms, right? Those of you that want to stay, do you think you have a higher chance of getting the car if you stay, or the same chance of getting the car, or what?
Well, I want if we stay on number 2, that means we went from 33% to 50%. So I would stay.
Okay, so you're saying that we used to have 33% because there were 3 doors, but now that there's only 2 doors left, we have 50%. Does somebody agree or disagree with that? And you can come in now, Christian, if you want.
Wouldn't it still be 50% chance no matter which one you pick? Since
It
there's
would
only
be
2 options
50%.
left.
Okay, so Jaden, I guess, agrees with Safa, right? That now that there's only 2 options left, it's 50%. Carlos agrees as well. So Christian disagrees, LOL. So Christian, why do you disagree? It's too late, Marco. Go ahead, Christian. You say you wanted to participate. Let's see. Christian says, I don't remember the last.
I think I think door number 2 still has the 33% chance. That didn't change because you picked that with 3 doors, right?
Uh-huh.
Sorry.
So then the third door, that's a 50% chance, but staying at the second door, that's still just a third, right? Maybe?
I like it. I like the way you think. Christian, do you agree?
I think you should switch.
Okay, good,
Because
good.
the option was eliminated.
I like that we're all thinking about this, right? And I like that we're thinking about it in statistical terms. So what do we have? We had 3 doors originally, 33% chance, a third chance in each door. But now we know that there is no car behind this one. Now, some of you say, because there is no car here, now the problem becomes 2 doors, 50% each. But those of you that say you should switch, right? Say, well, no, you should switch. Why is that? Well, originally, and here's when we started, originally we had a 1/3 chance for each door. The way we need to study this is we need to understand we picked a door and that choice has a 1/3 chance of being correct. If we pick door number 2, there's a 1/3 chance of door number 2 being correct. What's the chance of the other 2 doors, the doors that we did not pick, of being correct? What's that chance? We have 1/3 chance that door number 2 is correct. So what's the chance that door numbers 1 and 3 combined is correct? 2/3, correct, 2/3. So these 2 combined give you a 2/3 chance. When the host opens this door, that does not change the probability. The probability is still the same. It's still 2/3 that these 2, right, or one of these 2 has the car. However, we have new information now. The new information is that definitely it's not this one. However, the combination of these 2 still has a 2/3 chance. So if you think about it, staying gives you a 1/3 chance of getting the car, but switching now gives you a 2/3 chance of getting the car. So regardless of what your choice was, and regardless of what door the host opened, you always have a higher chance if you switch. Now this seems very non-intuitive, but remember, we're only talking about chances, right? That doesn't mean the car is definitely behind door number 3. It means that there's a higher chance of the car being behind door number 3. In fact, if we were to take an Excel spreadsheet, okay, so, oh, the chance was number of doors, not 50, this, and that's correct. The chance was always based on the original number of doors, correct. So that doesn't change. Just because we have new information doesn't mean that the problem itself changes. The system remains the same. The only thing that changes now is that you know that 1 and 3 have a 2/3 chance, and it's definitely not 1. So that means 3 has a 2/3 chance. So this is interesting because it doesn't seem intuitive. In fact, a lot of people did not believe this, right? A lot of people thought, oh, this does not make sense. It should be 50-50. If you were to plot in Excel every single choice of car, every single choice, first choice of door, every single choice of door that the host opens, and every single choice of switching and stay, and you get all the possible answers, you're going to see that 2/3 of your answers of switching actually gives you the car, and then only 1/3 of staying actually gives you the car. So yeah, that is the Monty Hall problem. It's actually a very, very interesting problem because, I mean, some of you understand this, some of you don't, that's fine. But for the most part, when this problem was first introduced, mathematicians did not understand this problem at all. They did not understand it at all. So even if you don't get it at the beginning, you do not have to feel bad. And you don't have to feel bad because, frankly, a lot of mathematicians did not get it at the beginning, okay? So it's a very, very non-intuitive problem. Maybe if we think of it in statistical terms or something like that, then maybe we can more or less understand it. But the reality is, the hard reality is that this problem is something that not many people understood, right? Especially when it first came out, okay? This is an example of how statistics can shed light on non-intuitive answers, because it's not until we actually get into the mathematics of it and start adding numbers to everything that we can actually see how it works. So statistics does help us look at things where maybe visually they may not be so obvious to us, but at least mathematically they become obvious to us. Now, I do want to take some time to talk a little bit about the importance of this problem. I mean, this problem was proposed and solved by Steve Selvin in 1975. And 15 years later, Marilyn Bossavant, a very, very, very brilliant person, right, received this question and also solved it. Because the question is counterintuitive, she received thousands, in fact, almost 10,000 letters talking about how wrong she was. Of those 10,000 letters, about 1,000 came from people with PhDs in mathematics and statistics saying that she was wrong. I would like to read to you some of these letters just so that you can see the arrogance of the typical doctorate degree holder, and just so that you know that now you know more than the person who wrote this letter. So, by the way, a lot of these things I mean everything. I don't agree with anything that I'm going to read, so don't take this out of context and then apply it to me. I'm not saying this. I'm just reading a letter that came from a person who wrote it, okay? Since you seem to enjoy coming straight to the point, I'll do the same. You blew it. Let me explain. If one door is shown to be a loser, that information changes the probability of either remaining choice, neither of which has any reason to be more likely, to 1/2. As a professional mathematician, I'm very concerned with the general public's lack of mathematical skills. Please help by confessing your error and in the future being more careful. This was Dr. Robert Sachs, professor of mathematics at George Mason University. I'll read another letter. You blew it, and you blew it big. Since you seem to have difficulty grasping the basic principle at work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There is enough mathematical illiteracy in this country, and we don't need the world's highest IQ propagating more. Shame! Exclamation mark. That was Dr. Scott Smith, University of Florida. I like Christian says, people were like this before the internet. I see, yes. People were always terrible. The internet just amplified that, but we've always been terrible. Another one, may I suggest that you obtain and refer to a standard textbook on probability before you try to answer a question of this type again? That was Dr. Charles Reed, University of Florida. Another one, I am sure you will receive many letters on this topic from high school and college students. Perhaps you should keep a few addresses for help with future columns. That was Dr. W. Robert Smith, Georgia State University. Oh, look at that, close to home. Another one, you are utterly incorrect about the game show question. And I hope this controversy will call some public attention to the serious national crisis in mathematical education. If you can admit your error, you will have contributed constructively towards the solution of a deplorable situation. How many irate mathematicians are needed to get you to change your mind? That was Dr. E. Ray Bobo, Georgetown University. Again, I don't agree with what I'm reading, and I need to specify that before I read this next letter. Maybe women look at math problems differently than men. That was Don Edwards from Sun River, Oregon. Another one. You made a mistake, but look at the positive side. If all those PhDs were wrong, the country would be in some very serious trouble. That was Dr. Everett Harmon, U.S. Army Research Institute. I actually agree with the doctor. The country is in serious trouble. But anyway, and finally, and again, this is also from Don Edwards. Disclaimer, I don't agree. I still think you're wrong. There is such a thing as female logic. This was Don Edwards from Sun River, Oregon. This just goes to show you, okay, that a PhD and tenure cannot stop you from making an ass out of yourself. So just want to make sure that we keep that in mind and that we remain or approach this topic with a certain degree of humility, because sometimes it's going to be, it's not going to seem intuitive. It's going to go, against everything we think, okay? And you'll notice that even people, right, people that have degrees and stuff like that, they can be arrogant enough to not understand statistics. Now, what's interesting is that after we explain it, it makes sense. But some people are just going to be unconvinced, regardless of how much you explain it to them. So just wanted to give you an example of how statistics can be, very, very helpful, because it is statistical analysis that sheds light on this non-intuitive problem. See you, Ramtim. I just read your chat message. Have a good one. So that's the Monty Hall problem. Okay, just give you an example. We're gonna look at other examples that are non-intuitive. They're not gonna be framed in the context of a game show. They're gonna be a little bit more engineering-ish. But just to keep in mind, it's important that we understand statistical analysis because things will not always come to us intuitively and quickly. Jaden, I think you are unmuted. Okay, thank you.
Sorry about that.
All right. No problem. So I'm going to do a second example, and this one doesn't really have anything to do with intuitive, non-intuitive. This one has a little bit more to do with sampling. Okay. So for those of you that know a bit about American history, 1948, Truman versus Dewey. You know that it was a very close race. I think everybody knows that it was a really, really, really close race. And the Chicago Daily Tribune ran a telephone poll of how people would vote. Call people, hey, how did you vote, or how do you plan to vote? According to the polls, and again, this is not just people calling people randomly. These were specific samples, prepared by statisticians that should represent the population. And Dewey won the polls, according to the Tribune. The newspaper published a headline, Dewey defeats Truman on the day of the election results. However, you know that we don't have a President Dewey, but we do have a President Truman. So Truman did win the election. And there's a famous photo of Truman on the day he won the election holding the newspaper that says, Dewey defeats Truman, and laughing. It's a really, really famous photo. You can look at it online. So what happened? Any ideas? What do you think happened here? Why did the newspaper publish that Dewey defeated Truman? They were very confident in their polls. What was wrong with the polls? Any ideas? No ideas?
Wasn't it something about them only pulling people through telephones and not accounting for a good chunk of the population?
That's a really, really good point, right? How did they take these survey results? By calling people on the phone. Who owned phones in those times? Well, it was only a certain part of the population there's only a certain part of the population that owned phones in those times. And what happened here is what we call sampling bias, because we had a biased sample, therefore our result was also biased. I hear that on the chat that same thing happened in the 2020 election. I actually think the same thing happened in the 2016 election. 2016 election was, people call it the biggest upset in election history because everybody thought that Clinton was going to win. Now, why was that? It's actually funny because it was the same reason, sampling bias. Okay, there's a lot of sampling bias, and whether or not it was on purpose or not, this is not the class to talk about it. It was that affected the final result. Now, of course, I don't think any of you are going to work in developing polls for news agencies. If you do, then God bless you or something. I'm sorry that your life turned out that way. But sampling bias is actually something that happens not just in the social sciences, but also in the physical and hard sciences too, and engineering as well. So whenever you are taking measurements and making observations, you need to make sure, okay, that whatever you observe is representative of whatever you want to apply your observation to. So because of that, let's come up with a couple of definitions. I am going to define a sample as the thing that I observe. And then those observations are going to be applied into my population. If I want to know what students think of a particular topic, I can't expect to get a response from every single student. It's actually easy now with the internet, but let's say back in the day. So instead, I need to find a representative sample of the population. For example, let's say that I want to know a student's preparation in mathematics. Engineering students' preparation in mathematics. Are engineering students prepared in math, yes or no? And not only that, I want to know their own perception of their preparation. I want to know how well do they think they are prepared in math. As a KSU faculty member, I could go ahead and ask KSU students to fill out a survey. And I can say that KSU students can be my sample. However, I want to make sure I know the student's preparation in math or perception of preparation in math for the entire student body and all engineering students. So if I take KSU as my sample, can I say, or can I apply it to the population that is all universities?
No.
In other words, why not?
There are probably some things that KSU students are more likely to do or experience that they wouldn't on another campus or another part of the world.
Okay, good, good. I like your answer, right? And this applies to everything, right? You can't just randomly say, I'm going to take this school and then apply to everyone. Renee says, okay, the Georgia school system, that's a little bit helpful. But even within the university system of Georgia, there's a big difference between, let's say, Georgia Tech and UGA, and then compare that to Georgia Southern, right? I'm not saying one is better than the other, although we already know the answer to that. But even there, the universities are actually so different that we can't actually take responses from KSU students and apply them to all USG universities. What we could do, however, is we could take responses from KSU students and then apply it, let's say, to all polytechnic, comprehensive R2 universities. Because KSU falls in that category, they follow the same syllabi, the same learning outcomes, and therefore it's expected that students will have a similar preparation. So being able to decide, right, what sample to pick and whether or not you can apply it to your population is very important in statistics. And it's crucial because it's one of the first steps you make. And if you get it wrong, you're not going to get the correct answers. So this is something very important. Whenever we're looking at collecting data, we need to first understand or recognize whether or not our sample is representative of our population. Suppose that you want to understand a little bit about bilingual education, and you want to talk to students who have studied or a second language. Would you have better luck running your survey in Texas or in Wyoming? If you're trying to study students that have learned the second language, Texas, right? Because definitely there are far more Spanish speakers in Texas, right, than there are in Wyoming. And if you look at different stats, obviously Spanish is definitely the non-English language that's most spoken here in the States. So that's why I'm using Spanish as an example. So that all comes into play, right? If I would have started straight up in Wyoming, I would have immediately gotten my results wrong, right? So it's very important to understand your sample, to understand your population. You look at different universities, and there's different trends. I'm not saying that these trends are true for all, but I think it's very clear that the Kennesaw campus is more liberal than the Marietta campus, right? So depending on what information, let's say you're trying to get surveys and opinions for a political poll, right? Whether or not, depending on which campus you go to, you're gonna get far different answers and far different results. By the way, I feel much more at home at the Marietta campus, if you needed to know that. So we need to understand all this, right? Understanding our sample, it's crucial for applying our results to our population. Now, you've all heard the saying, right, that a good liar is a statistician, right, or a liar is a good statistician. And even though statisticians don't like that because they feel it's a little bit demeaning to their profession, it's actually true. If I want to prove a point, any point, I can easily make that point by being selective on my sample and my population. So even though I am using the correct methods, the correct equations, asking the right questions, I can easily manipulate my results by modifying the sample and the population. So if I'm doing everything correctly in terms of statistics, right, equations and stuff like that, then can I still say it's a good statistical analysis? I would say no. I think the goal of statistics should be to present data in the most unbiased way possible. Is that really what happens? I don't think so. I think that everyone, even maybe even myself, maybe I don't realize it, but I think everyone always throws in their own biases into the information they present. And that can be something as subtle as maybe emphasizing a couple of things more than others, right? Something subtle, but our biases are everywhere. So then if that's the case, why would we learn statistics? Like if it's just teaching us how to lie. So since that is the case, I would say that statistics becomes important, right? Because it should help us understand our own biases so that we don't, or so that we are not affected by them when it comes to making decisions. So I'm going to try my very best to be as unbiased as possible in this class. But those of you that have taken class with me, you know that I like to add a lot of color commentary to everything I say. So bear with me, right? It teaches us to see when other people are skewing the results. Yes, I agree with you. And sadly, that happens more often than not. So I would say it teaches us to see when other people are not skewing the results. And we mean, oh, look, these are actually unbiased results. Christian says statistical literacy is a must in these days. It is. In fact, what I'm going to do with the project, like I said, the project is divided into different parts. What I would like to do for the project is not just to get you to apply equations and stuff like that, but you'll notice that in some parts of the project, I'm actually going to ask you to lie. I'm going to say, hey, take your conclusion, but now show me the opposite, the complete opposite of your conclusion, using the same data. So I will ask you in the project to lie, and not because I want you to be a liar in the future, but because I do want you to be able to recognize it. If you know how to do it, then you'll be able to recognize it when other people are doing it. So let's just keep that in mind. Sometimes in a project, you'll be doing some things, and then I'll ask you to show the complete opposite, even though you have the same data. And it's not impossible. It's actually very possible and very easy. And once you learn to do it, you'll be able to learn how to identify it when you see it, okay? So we've talked a little bit about statistics. I would say the focus of this class will be definitely to solve problems, right? It's not really to teach you how to lie. It's to teach you how to use statistical methods to solve different problems, okay? So in this class, I want to use I call it the Ppdec, but it's actually not called the Ppdec. It's actually the Ppdec, or Problem Plan Data Analysis Conclusions. But I use the Ppdec model to apply the scientific method. And the Ppdec model is a very simple model. It's something that's really commonly used everywhere. And let me just write it here. Oops, Ppdec. And it consists of defining and understanding your problem. So you want to define and understand your problem. So before you even try to solve anything, you need to understand it. And how do you know if you understand your problem? Well, try to define it. Try to explain it to someone else. And you'll notice you learn a lot when you try to explain things to other people. I learn a lot when I teach. And I don't like to admit it, but it's true. I do learn a lot when I teach because it kind of forces me to break things down for myself so that then I can carry that information to other people. Once you define and you understand your problem, then it's your time to plan out your solution. You need to know what it is you're going to do before you do it. You can't just randomly start throwing numbers at your problem and hope to solve it. Planning involves things like figuring out what your sample will be, what your population will be. But even beyond that, you should at least know how you're going to analyze your data ahead of time so you know what data to collect. The third step is to collect your data. And that can be done in a number of different ways. We're going to talk about those later. Then to analyze your data. And finally, to draw conclusions. So the Ppdec model is kind of what we're going to try to follow in this class. It's not a rule. You can definitely switch the order around if you want. But the important thing is that before you try to solve something, you need to understand the problem. And before you start collecting data, you need to plan out what you're going to collect. And then, of course, collect and analyze. And again, these two can be interchangeable, and your conclusions should eventually follow off from the analysis. Okay. Remember, statistics is the collection, organization, analysis, presentation, and interpretation of data. And all those things kind of fall somewhere here. Okay, all those things. we're going to focus in this class mostly on what happens after we collect the data, because of course I'm not going to force you to take a survey or something. I know that there are TCOM classes that students have to do surveys and stuff like that, and that even though it's fun, it does become a bit of bother, because most students, all they do is they just make up the answers, and that's not fun. So instead of this class, we will definitely focus on the analysis portion, right? But we also want to talk a little bit about what conclusions we can draw from those analyses. Now, one thing we will learn in this class, I'm not going to force you to, I'm not going to give you, right, a method, or I'm not going to tell you how to interpret your data. I am going to leave that up to you. Because even though we follow the same methods, perhaps how we interpret our results may vary from person to person. I'm not saying that that's wrong. I'm not a relativist. I definitely believe that there is one objective truth. However, I can't really come with the assumption that I have that objective truth, right? So because of that, interpreting data will kind of be up to you, and hopefully you will be able to use the scientific method and other things that we learn and practice in this class in order to interpret your data. So this will be the method that we're going to use to solve our problems, the Ppdec. And then we are going to apply something that's called statistical thinking to our approach. Now, statistical thinking is something that doesn't just apply to this class, it applies to everything. And statistical thinking is essentially a nice fancy way of saying, hey, think statistically, right? You incorporate your variability in your decision-making process and your problem-solving process. Statistical thinking, again, doesn't just apply to this class. You should always be thinking statistically. You know, whenever you're making any decision, you are thinking statistically. So the idea is take that statistical thinking and now apply it to this class. So I'm not asking you to do anything new. I'm asking you to take your critical approach, how you approach decisions and risks, and I want you to bring that into the class. Okay? I'll give you an example. I was an engineer. I mean, I am an engineer, but I was an employee at an engineering firm several years ago. And part of my work involved doing some field work. And on field days, we had to go through several locations, about 100 different locations, maybe not 100, about 50 different locations or 40 or 30 different locations every day, and then collect about 100 data points. These were storm sewer measurements. Now, the locations were all spread out, mostly in Gwinnett County, and my office was in Atlanta. So I had to drive from Atlanta to Gwinnett County and then just kind of like drive around Gwinnett County to get the different measurements and then drive back. So obviously, we want to make sure that we can, we want to make sure that we can optimize our routes. So let's say I'm in my Atlanta office. I have a couple of locations in Gwinnett County. I want to know what is the most optimal route that I can take. So what I did, what people typically do is just write everything on Google Maps. But on Google Maps, it doesn't really tell you where to go first. You need to tell it where you want to go first. Now, you could do all the different options and then figure out which one has less time, but that's not really helpful. So what I tried to do is I came up with a small little algorithm that would figure out the distance, driving distance, not horizontal distance, but the driving distance between the different points. And then it would just do a little bit of machine learning and a little bit of iterations in order to optimize itself and figure out what the best route was, the route that would give me the shortest driving distance. And we did that, and I used my little algorithm to plan out my trips. I was very proud of myself. I pat myself in the back. I was like, wow, I'm a genius. but there was something I was missing. So this optimal route thing that I wrote, it only considered driving distance, and that's it. And yeah, it worked fine for my own purposes. But if I wanted to scale it, if I wanted to say, hey, this is what postal office workers and delivery vans should use, I'm actually not right there. I'm actually wrong. Because even though this does consider the shortest driving distance, what do you think I'm not taking into account? Do you think there's anything else I should take into account to figure out what my optimal driving route is?
Traffic.
Traffic. Good.
Yeah.
Exactly. I need to take into account traffic, and traffic is not a constant thing. Traffic changes with time. Of course, if I'm driving at 6 a.m., I'm not gonna run into that much traffic, especially if I'm driving against rush hour movement. But then during school hours, traffic becomes pretty bad because you have school buses, right? During rush hour at the end, trying to drive back, traffic becomes very bad. Stop signs and traffic lights, says Renee. That's absolutely right. I need to consider all those, right? Speed limits, says Bailey, and weather, says Sarah. All those are absolutely right. All those things that I should have considered, I didn't. So even though my little algorithm was nice for a one-day field trip, it wasn't something that I could scale into something bigger. So I took my pats in the back because there was a lot more that I needed to consider. So statistical thinking takes that into account. So statistical thinking is me saying, okay, what do I need to consider? And then writing down, okay, I need to consider not just distance, but also traffic, but also, I'll just call them intersections. So stop signs and traffic lights, weather, okay? And if I want to be very, very optimal, I even want to consider my own car's mileage. Okay. What car should I take? Should I take my car? Should I take the company car? What gives me a better return, right? So all these things have to come into play here when I'm actually trying to come up with this optimal route. And if I don't consider all of these, then I'm not really doing statistical thinking. If I'm just looking at this in terms of distance, which is what I was doing, I'm actually looking at this in a very, very one-dimensional way without taking into account the dynamics of everything else that was going to affect my travel time. So I think you're all very much aware of the different aspects that come into play in statistical thinking. You want to consider everything that could affect you, could affect your system, and then you figure out, how can I measure them? How can I take them into account? For example, how can I take into account traffic? Well, probably you can take them into account with time. At different times, traffic is different. So even though you can't predict what traffic will be like specifically on a day, you can say, well, it's a weekday, so perhaps 8 a.m., 5 p.m., there's going to be more traffic because of rush hour. 2 p.m., there's not going to be too much traffic, but driving in neighborhoods will be slow because of school buses, right? Stoplights and stop signs and stoplights, right? What do we consider? Well, one thing that is it delivery vans or postal office workers, like they don't turn left or something, so it's like no left turns because it's actually faster to just turn right all the time. So things like that can come into account when I consider my intersections. Weather, when is it better to be in the car? When is it better to take measurements? If I arrive at a measuring location and it starts to rain, I can't measure. I need to wait in the car. So I want to make sure that I'm driving when it's raining and that I'm measuring when it's sunny. But when it's raining, traffic typically runs slower. Georgia people don't know how to drive, so whenever it rains, they drive really, really slowly. So I need to take into account that, like how is that going to affect? So all these things, right? All these things are going to make my analysis very, very complex. And the idea behind statistical thinking is being able to consider them. It doesn't have to be perfect, but at least they all need to be considered. That's what we're going to try to apply into this class, statistical thinking. So don't just take my word for everything. You always want to think, what else will affect this? If I ask you to come up with number of parking spots, right, or a number of available parking spots, and I only give you 2 variables, don't think that those are the only 2 variables that are going to affect, right? You always want to think of all other things, like how many stores are there? What's the average age of the people living near that, near the strip mall where you're designing your parking lot, right? All these different things. Are you gonna put in a nice little community center with weekly bingo in a place where it's mostly young people that live? Probably not, right? So you always want to think of all these things, right, as much as you can, everything that can affect your system before you actually try to study or design or analyze your system. Now, in order to kind of move forward and talk a little bit more about what this class is going to be about, I do want to come up with more definitions. Every now and then, I'm going to interrupt the class to give some definitions, and I apologize for that, but I also want to make sure that we're all on the same page here when it comes to talking about things. So in this class, we're going to talk about our systems, our projects, our problems. We're going to talk about them in terms of experiments. So an experiment doesn't necessarily mean that you get a lab coat and then you measure how some chemicals mix. No, an experiment in statistics is anything that has more than one possible outcome. The book calls it a random experiment, which is also a good name, but all experiments are random, so I'm just going to call it an experiment. Okay, so anything that has more than one possible outcome. Is that the rank of occurrence? Does occurrence have one word or an R or two R? I think it's two R's. Okay, so anything that can have more than one outcome is what we call an experiment. An experiment can be as simple as rolling a die. It can be as complex as, you know, I don't know, studying the structural dynamics of a space ship. I don't know. It can be as simple as you want, as complex as you want. So anything where there's more than one outcome, we in this class are going to call it an experiment. Okay. Now, experiments are going to consist of random variables. Now, in this case, it is important that I use the term random because not all variables are random. So a random variable is a variable in our experiment that can have more than one possible value. So any variable with more than one possibility. For example, I flip a coin. My coin can land in heads or in tails. I can say that my random variable consists of what the coin lands on, heads or tails. However, experiments can have more than one random variable. Another random variable for my flipping a coin experiment can be the time it takes for the coin to hit the ground. Okay, that's another random variable, and that time can be whatever, 1 second, half a second, a third of a second. That's correct, Bailey, right? Another random variable could be how many times does it bounce? Once, twice, 3 times. Another variable could be what's the frequency of the noise it makes when you flip it. I mean, random variable is anything in your experiment that changes. It's important to recognize what the variables are so that you can determine which ones you want to consider for your experiments. I said that experiments have more than one outcome, and therefore we can define outcomes as our possibilities, our results. So our outcome is essentially a combination of one or more random variables. For example, we flip a coin, and let's say we want 2 random variables. We want to know if it falls on heads or tails, that's one random variable. We also want to know how long it's in the air. That's another random variable. My outcome is those 2 random variables combined. Did it fall on heads or tails, and how long did it take? That's the outcome. So an experiment can have multiple outcomes, and outcomes can be combinations of the different random variables. And then samples is essentially the set of all possible outcomes in an experiment. I apologize for my less than stellar handwriting, but you have all this in your notes anyway, so you can copy it from the notes. Okay. So the set of all possible outcomes in an experiment is my sample space. So my sample space should include every single possible outcome: heads, tails, how long was in the air, 0 seconds. Let's say it never went to the air, right? Like 0.1, 0.2, it's everything. Everything is in our sample space. And finally, an event is a subset of the sample space. So just a combination of values from the sample space. Now in this class, it's going to be very helpful to approach these variables graphically. Now we're going to deal with random variables numerically in the future, possibly after week number, maybe during the 3rd week of class. But sample spaces and events, it's actually a little bit more helpful if we visualize them graphically. So instead of thinking of sample spaces as lists of outcomes, instead of thinking of it as a list, think of it as an area, where this area represents my sample space. So all possible outcomes have to be inside this area. So we want to think of it graphically, like an area where all the outcomes, like tails 2 seconds, heads 1 second. Everything is inside here. Now, why is it necessary to do it graphically? Because sometimes our random variables are infinite. If you're measuring time for something, the possibility can be infinite. It can be as low as 1 second, as high as I don't know, like millions and millions of years, right? Let's say, depending on what you're measuring. So the sample space is an area that contains all of your outcomes, and therefore an event is a subset, right? A small group, I'll call this E for event, a small group of values within your sample space. The reason why it's important to visualize it graphically is because we're going to look at combinations of events, we're going to look at unions of events, we're going to look at different ways of manipulating these events mathematically, and perhaps it's better to visualize them graphically instead of just going straight at them numerically. So always consider sample spaces not just as a list of things, but as an area where all my outcomes are inside it. And then an event is, again, not just a smaller list of things, but a smaller area within these sample spaces. So we're going to use a visual approach, and we're going to use mathematical set theory in order to understand them. But don't worry too much about that. We're going to review set theory on Monday of next week, so don't worry too much about it, okay? So in statistical analysis, I already mentioned that we typically study a sample, and then we apply our conclusions to the population. But I mentioned that there's actually 3 ways of studying a sample, right? There's 3 different ways of collecting data, and I want to talk about those 3 different ways. In this class, we're gonna focus on probably on the first one or the first 2, but there are definitely 3 types of studies. One is what we call a retrospective study. And retrospective study just means that we're looking at historical data. So we are looking at old data, graphs. Let's say graphs from the 1900s to 2000, I don't know, GDP or something, right? We're looking at things that happen. They already happened in the past, which means that even though we can see as far as data is available, we also have a disadvantage of we can only observe what has already been recorded. So perhaps we are studying GDP, but for a specific year, GDP was not recorded. Well, we don't have it. We can't go back and get it. Or perhaps we're studying GDP, but we also want to know GDP as a function of, let's say, as a function of unemployment. And perhaps we don't have the unemployment data, we only have GDP data. So retrospective studies, they give us the advantage that we can look at whatever we want, however long we want, but they give us a disadvantage that we only have the data that was recorded available to us. We have what's called observational studies, which are when we are studying something as it happens. For example, you may do this I don't know if you do this in your traffic, do you have to take traffic engineering? Maybe you don't. But when I was in college, I had to take a class called traffic engineering. And for that class, I would take this little clicker thing, and I would sit down at an intersection and count all the cars that went through the intersection. So we had our intersection here, and then if a car moved from here to here, I counted it. If a car moved here, I counted a different clicker. If a car moved here, I counted. So I was always counting cars. We always had to do this for our traffic engineering classes. So in an observational study, you are actually looking at things as they happen. Now that gives you the advantage that you can measure or observe whatever you need. It also gives you the disadvantage that you are only limited to whatever you can access at that moment. In other words, if I go to observe on Tuesday, but I want Monday data, then I didn't get it, so I lost it. So observational data. And finally, the last type of experiment is what we call design experiments. And a design experiment, that's where you come into the lab code. That's when you come up with the, is this a lab code? Yeah, it kind of looks like a lab code. That's when you come up with the experiment yourself, and then you are observing something that's happening in a controlled environment. Okay, so design, oh my God, my stick person looks terrible. A design experiment is where you are controlling the experiment. I am controlling the temperature, for example. I am controlling the light or whatever. I am controlling the volume. So I'm controlling everything. Now in this class, we're not going to do any design experiments. We're going to focus mostly on retrospective experiments because we're going to look at data from the internet, and I'm not going to force you to go. Actually, See, if I had a little bit more spite for you, I may force you to go to an intersection and count cars, that was like one of the worst college experiences I had. I mean, I would have had fun if we could just go with a couple of friends, sit down there, and then just do this experiment together. But the professor was smart. The professor made sure to give us all different days and times to go there, so that nobody was doing the same thing at the same time. Which means that when I went there, nobody else had to be there. And when somebody else was there, nobody else was there. So yeah, I'm not gonna make you do that. But if I did have more spite for you, or if you make the class hard for me, I will turn this into a part of the project. That's the good thing about being in power, is that you can make things to your own advantage or to the disadvantages of others. Okay. So in this class, we're going to focus on retrospective studies, but you need to understand that there are definitely disadvantages that the observational and design projects will definitely be able to address. Carlos says, my boss said he had to count cars back then at Southern Poly. I had to do it too. I didn't go to Southern Poly, but I feel when I was in college, it was kind of a given. Every civil engineer student has to count cars. That's like, you have to do it. I think nowadays with accidents and stuff going on, like it's a little bit harder. But back in the day, it's like, yeah, my friend got run over by a car. He's no longer with us. Okay, let's move on. But nowadays, you got to be a little more careful, of course, with all those things. I had to bird watch for biology at my previous university. Actually, bird watching is not bad. It's actually fun. I enjoy it. So I may make you watch birds then, or something, or just like go to the quad and watch nerds or something, and then take measurements of nerds. Like, what are you doing? We're measuring. What are you measuring? Observing or whatever. I'm observing nerd behavior. I don't know. I'll figure something fun, but I really don't want to force you to go out for this class, because it's not a class that you nerd watching. I love that term. Nice. I'll think about applying that into the class, but this is not a class where I want you to go out and do things. It's more of a laid back class. I want you definitely to learn about statistics. I'm not gonna force you to do a really big, really difficult project, but keep in mind that there are different types of studies, and this class will focus on the retrospective study, okay? Now, I keep talking about data, collecting data, analyzing data, science of data. What is data? Can anybody tell me in your own words what data is? Information, gathered information. Okay, that's good. Information collected during that event. Okay, I like those definitions. That's good. But what makes them data? I mean, information can be anything, a collection of information. So how do I know that I'm looking at data or not looking at data? It is a fact. I don't want to get onto the philosophy of what facts are.
So from what I understood, I think that data is any type of information that you gather to actually, I don't know how to put it in words, but in a way that it's any type of information that is gathered for a survey or statistic, anything that would help us find something else in a way.
I like that definition. I do think it's a little bit redundant, because this is a statistics class and you're going to use data for that. But I like what Christian said too, quantifiable. Data is quantifiable. And we need to keep in mind that not all information is quantifiable. So what we call data is that information that that can be quantifiable. So for example, I can ask for something, right? Like, describe how much do you love your pets? And you can give me a description, but unless I find a way to quantify it, then it is not data. However, if I give something on a scale of 1 to 10, how much do you love your pets? Or on a scale of not a lot, I love them more than I love myself, how much do you love your pets? Then that's when it becomes data, when I can quantify it, okay? So data is information, yes, it is information, but it's specifically information that we quantify. And when I say quantify, I'm not talking specifically about numbers. It can be anything like colors, and red, blue, yellow, that's quantifiable. Doesn't have to be numbers, but the idea is data is something that we can quantify. And in this class, we are going to deal with data. So we're going to be dealing with information that is quantifiable, information that we quantify. Before we finish today's class, we're actually going to finish a few minutes early. That's actually great. Before we finish today's class, I do want to explain a little bit about what the purpose of statistics is, right? So we talked about why we need it, how we can use it, all that stuff. But from an engineering perspective, I know that I've been a little bit lazy with the engineering applications on this first day. But from an engineering perspective, we collect data to create empirical models. And empirical models are essentially models that come from gathered information. Now, that's very different from mechanistic or theoretical models. In that, theoretical models, you start with a law, you express that law mathematically, and then you come with that, you use that math, right, to derive some equation. Then you use that equation to predict what's going to happen. We need to know the theory in order to come up with a prediction. Empirical models are not like that. Empirical models, we don't know the theory, so we actually start with observations. We start with something that's happening, then we use that to create the equation, and then we use that equation to predict. So theoretical models, they don't need observations. Empirical models require observations. It's pretty interesting because when we think of something like, you know, the difference between a theory and a law, of course, laws or physical laws are observed phenomena that are given, right? They occur. We don't know why, and we don't want to know why. We just know that they are always there for the entirety of the universe. Of course, we found that some laws, like Newton's law of gravitation, turn out to be not exactly correct, and we've had to, you know, modify them or refine them with, in this case, with relativity theory or with quantum theory, which is something that's pretty cool. That's where they're trying to reconcile gravity with quantum theory. That's pretty cool. But anyway, in terms of empirical observations, we don't have a law that we can follow. So instead, we look at observations and we come up with our equations that fit those observations. And maybe they'll work, maybe they won't. How good those equations are is what we're going to talk about in the last week of. Sorry to keep you waiting. But during the first couple of weeks, we're going to focus on how to study these different phenomena, how to apply different statistical methods to them. And then at the very end, we're going to be using the most popular regression method, which is linear regression, in order to actually come up with our own predictions. That's a little bit of an introduction to statistics. I hope that you enjoyed it. I'm not really, I won't feel bad if you didn't, because it's definitely not, for a lot of us, it's not a subject that we want to learn. But believe me when I say that this subject is going to be very helpful, not just for your engineering careers, but for your lives in general. Because statistical thinking is important. I think there was a student earlier that said that statistical literacy is pretty much a given, right? It's really, really important. And I agree with that student as well, right? It's super important. It's something that's going to help you not just with your engineering careers, but even with your day-to-day decisions. Okay, you know, should I get married at this age? Should I move to this neighborhood? Should I take this job? Should I finance this car, this expensive car, or buy this cheap car? It's the latter, by the way. Never finance an expensive car unless you are writing it off for tax purposes. But anyway, all those things, right, require statistical thinking. And hopefully, my hope is that this class kind of gives us a little bit of an introduction to the terms. I will warn you, a lot of the material in this class is very dry. We're going to talk about probability distributions, different types of random sampling distributions. We're going to talk about a lot of terms, a lot of equations. So at times, the class may seem dry, and that's okay. I'm going to try my best to keep it interesting, to go back to interesting things, but I will warn you that sometimes it will seem dry. So you'll just have to bear with me until we get to the fun parts, which are scattered throughout the semester. I thought instead of putting the fun parts at the beginning or at the end, I tried to scatter them throughout the semester so that we can kind of get a little bit of refresh, okay? So that being said, let's end the class now. I will see you on Monday. And what I'm going to do, by the way, fill out your survey on the syllabus, and I will organize or prepare a list on D2L of who's showing up to class in person, who's going to stay online. Look at that list. It'll be posted over the weekend. Look at that list so you know when you're coming to class and when you're not coming to class. I'm not going to force you to come if you want to be fully online. But if you do want to come in person, you'll only be able to come if there's enough space for everyone, which means that, you know, if you want to be fully online, then you're online. But if you want to come in person, you got to look at that list, okay? So look at that, and I will see some of you on Monday, and I will see some of the others on Wednesday. Okay. Get the book. I'll also start finding a group. I don't recommend that you do your homework on your own. Do it in groups. It'll be much more helpful. Okay. Only one submission per group for everything. Homework, projects, everything. Only one submission per group. Okay. Are there any questions?
So do we just write the names of everyone in the group on the homework?
Yeah.
Okay.
Yes. All right. All right. Have a good weekend. I will see you on Monday.
Thank you.
You're welcome.